start recording. Okay, so we have g of x equal minus f of x. So I'm going to take as an example for now, and this is just a reminder. Okay, always think of f of x as your y. So if I take the parent function, which is f of x equals x squared, what do I expect to happen with g of x? How can I write it out algebraically? I can take any parent function, but I'm going to focus on just the x squared. What do you think will happen? I know it's minus f of x, so what would I need to do there? Okay, I'll give you this one. We have negative x squared. Okay, so I have the negative, and the function itself is just x squared. I'm just highlighting the brackets there, but they're not necessary, right? Because it's a multiplication. So the function itself is just negative x squared. Okay, that's reflected into the x-axis, f of x, right? So now if I'm going to label this one here f of x. That's the original quadratic function. What do you think the other one would look like? It's all reflected. Upside down. Okay, so I take all the points. The vertex stays fixed, but all the other points go to their negative value, right? So if I take a few points, we all remember the 1, 1, and the 4, 4. What value will they go to with the reflection? A negative, right? So I have a negative 4, and I have a negative 1. And that there is now my g of x is equal to negative x squared. Okay, and I have to label this. This is g of x. So g of x is the reflection of f of x into the x-axis. And I'm only highlighting these points because they do help you if you think in terms of the table of values. We can also do this visually, right? All the y values go to their negative. Okay, so I'm going to stay with this function with the x squared, but now I'm going to go to f of negative x. Okay, so this one here. What do you think will happen here? What type of reflection will that be? Oh, hand up? Is that a hand up or just?
Oh, yes. It's going to instead of doing the x-axis, we're going to
Yeah, about the y-axis. That's right. So all the x values go from the positive to their negative, and the negative ones go from negative to the positive. Okay, so it's a reflection about the y-axis or into the y-axis. Now we're not going to see much happening in the case of f of x being x squared. So here I have g of x that's simply negative x squared now, right? But that negative, when I square it, what happens with it? Minus 1 squared gives me a positive. So that's why I can show it algebraically, but we'll see graphically too that nothing changes for this particular function if we just reflect about the y-axis. Okay, so the quadratic is a special one. Okay, so I'll start with the parabola again. We have our 1, 1 and our 4. So that's just the f of x. And I will use a different color, but the idea here is, let's say the orange point's on the right. Okay, I'm going to transform this so it's going to go reflected into the y-axis. So we're going to move over to there. So that point will now go to this here, and then this point will go here, and vice versa, right? So it's an identical function. I'm just going to overlap it. Okay, so in this case, g of x is equal to f of x. But I have done a reflection into the y-axis. Okay, it's there, it's just not terribly visible. Okay, and the last step is this one here. So how many reflections am I doing in the third case here? 2. Okay, and does it matter, do you think, what order I do them in? If I go with the horizontal versus the vertical? No, it doesn't, not in this case, okay? So once we get into other operations, it will, but for multiplication and division, it doesn't matter. So we'll say here into the x and the y-axis. And y-axis. So we can take this algebraically again. We have a negative and then a minus x squared. Right, so I'm replacing the x with a negative x, and I still have a negative outside the bracket. The first one goes away because of this square, so we have a negative x squared as the final g of x. Okay, so it looks identical to the very first one that we did, right? Which isn't of any surprise because nothing happened under the reflection into y. So let's do a quick graph, which should look exactly like the very first one we have. So this is the f of x. So if I first reflect across the y-axis, it stays identical, and then my second step would be to reflect into the x-axis, and we're getting our reflected negative f of negative x, which is our g of x. So I'll give you a minute to try maybe the radical function, but I will do it with you. Okay? So the same idea at the bottom here. We're going to take f of x as, what was the radical function? Square root of x. Okay. So first I can get an expression, which is negative root x. And again, what changes here if I have negative f of x, reflection into the x or into the y? Into the, x-axis. So remind yourself the y is changing, right? Y changes, so reflect into x. So if I take the main points here, again, we have the 1, 1, and we have the 4, 2, and the 0, 0. So where would those go? Would anybody like to come to the board and show where those points go after the transformation? Okay, Rebecca? It's exercise time. Yeah, well, no, just point, and I'll draw them. It's not a smart board. Where? Yep. And so it would be a negative 1, and so a negative 1 and a negative 2. So what do we notice about the starting point? It's the same, so that we'll learn later what it means, but for now, f of x, just note that the starting point usually stays the same, and we have our g of x. Okay, and this was a reflection into the x-axis. So make sure you recognize it in both forms. So algebraic, it's minus root x, right? And graphically, you should know both of them. Okay, do the next one independently. I will pause this, and let's see if you have the same answer. Yeah. Sorry? About the next one? Sure. Yeah, you do. It is possible. It's just a different way of writing things. Okay, we'll go over what that means. Remember when we did inequalities, we switched the signs if something was negative? Okay, so it just goes in that direction. Okay, nothing's impossible. Okay, so we have y. And don't forget the original function, the parent function, should be drawn first. Yeah, are we ready to take it up? Everybody good? Okay, 2 more minutes. Yep. G of x? No, it's in this case, you mean? This particular case?
Yeah.
No, because I see why you're getting confused with the negative x, but we'll talk about that. That's right, what you have. That's the right expression. Okay? It just means you have to interpret it a bit differently. Okay? We'll write it exactly as we recognize it. So let's see here. Is everybody done attempting this? Should we reveal the... Okay, big answer. Okay, so we have the graph there. Now, all this means, I'm going to do it in gray, just so we're not... You don't have to do this every time, but I'm writing here the negative x here has to be greater than or equal to 0, right? All of that quantity has to be greater than 0. So all this turns into is that x is actually less than or equal to 0, right? Because if I say negative 2 is greater than 0, then 2 has to be less than 0, right? So the values have to be inverted. So all that means is instead of being on the right side of the y-axis, I'm actually going to the left side, right? So I'm taking all those points, and what color did we? This one. So I'm going to a negative 1 and a negative 4 on the other side. But once again, the origin stays put, okay? So this is my g of x now, which is root of negative x. So a reflection into what axis? Into the y, okay? And the last one, would anybody like to come to the board to attempt this one? What color should we pick? Too many options. We haven't used yellows, but... Sorry, yellow? Okay. Okay, so let's say, I still need the blue for a bit. So we have g of x is now, what would the expression be, the final expression? Yeah, Del?
For the second function, if
Oh, you asking a question?
yeah,
Okay.
if negative x means it's 0 or like larger than 0, then x is less than 0.
Yep.
Then when you do negative x, then shouldn't the x?
Because you think of negative minus 1, for example, which becomes 1, right, when you take the radical.
Mm-hmm.
So you always have the negative there to buffer, in a way, the negative values of the numbers themselves, right? The x is negative, but then I'm putting a negative, so that all of that is positive under the radical.
And then when you like plot it in a graph, would you plot it with like the negative x coordinate or the x coordinate?
You are. This is the negative side.
Yeah.
So this here.
So these would be x though then. Because if x has to be like a negative,
Yeah.
then these would be the x coordinates and these would be negative x. So should we be
No,
plotting
no.
it here?
No, so I think you're thinking of it backwards. This is positive, x is negative. So I'm just going with the same point. Maybe we'll do a table of values just to convince yourself.
Okay.
Just 1 second. I'll go back to that, but let's just finish. Okay, so we might need to do a double check with the table of values, but for now the expression is negative root of minus x, right? So I still start with the reflection. The easy one would be about the x-axis, let's say. So that's the minus at the front. So if we break it down, let's say 2 colors. So this one would be into the x-axis. And the second one, this would be into the y-axis. Okay? So we have those two. So if I reflect first into the x-axis, I'm going to end up here. So I'm not going to write it in full yet. I'll simply write down y is equal to negative root of x. Okay, so I've only reflected into the x, and now I'm going to go with the second transformation, and we have into the y. So all these points go from 1 to negative 1, from 4 to negative 4. So this is my final g of x. Yeah, I've only drawn the yellow one is the intermediary one. Right? This, you don't have to, no. But I'm showing the steps. So first I operated on the reflection about the x-axis and then about the y-axis. Okay? You don't have to show the yellow one. But once we get into multiple transformations, it's a good idea to at least draw out the points so you can guide yourself through the transformations. Okay? Not the full function, but at least these ones here, so you know which way you're traveling. Okay? Okay, so someone was asking about this one here, still not convinced that root of negative x is where it belongs, right? So let's take the first point. So I have a minus 1 here and 1, right, as the point. And the expression of the function is y is equal to, I'll write it here. So we know that y is equal to root of negative x. Okay? Now does that make sense? If I check my values, I have y for 1, and then I have a negative, and then the x is also negative, right? Does that check out? Okay? 1 is equal to root of 1. So you can do that through a table of values if you want to, but visually it will always be placed in this quadrant, right? So always on the left side. If I say that negative x has to be greater than 0, then x has to be less than 0. But the negative doesn't go away. I'm just treating the domain. That's what I'm doing at the top. I'm just explaining what's happening with the domain. But the negative stays there in the expression. So if I go to the negative values of x, that negative is just a buffer for all the negative values, right? Minus 7, minus 3. Okay, so it's root of a positive. Okay, so if you guys understand all of this, easy, right? Yeah. Okay, so all that this is it's a change in, let's say, y while the x remains fixed, or a change in x while the y remains fixed. So you can graphically, this is the easiest way to remember it. Y to x and x to y. Okay? So direction, it usually takes place across the x-axis or across the y-axis. There are other reflections, and we'll look at that in a bit. Especially remember the inverse function, so we're doing a reflection into the y is equal to x-axis. That's the transformation we'll look at the end. Okay? But that's also a reflection for now, just into the x and y. Yep? Exactly what I said at the top. So it's a reflection into the x and into the y-axis. So you would have a 2-layered transformation. So what we wrote here is just written up there. Okay, so it's just 2 transformations in one. We can say here for now. Okay, let's see what happens with stretches and compressions. So we'll go through examples because this is the best way to see these things usually. So for the radical function, what do I have here? F of x is equal to root x. Do we recognize that? What is it called? The radical function? Okay. So if I have radical x, let's graph it. We have 0, 0, 1, 1, and 4, 2 as a reference. And for this one, we can go through a table of values in just a bit. But let's just look at what happens with g of x here. So if I wrote g of x in terms of f of x, how would I rewrite that? So I know f of x is root x. If I take the root x away and I replace it with f of x, I notice that that's a 2 times f of x, right? So again, I'm looking at y values. This was the original y value from the parent function, and this is the new y value for the transformed function. So if I go 2 times the old y, what have I done there? Have I changed the y or the x? The y value, right? So whatever was before goes to double its original value. So that means this here, whenever I have it in front of a function, would be a vertical stretch. Right? Is that theatrical or?
Yes.
Okay, so vertical stretch because the y changes. So y changes while x stays fixed. And we'll convince ourselves through a table of values. So if we go with f of x and g of x. Okay, so we know roughly where this is going to go. The 0, 0 stays put because 0 times 2 gives me a 0. 1 times 2 gives me a 2. And a 4 times 2 gives me a, what is it? 2 times 2 gives me a 4, right? So all these points actually go to double their original y value. And we don't have to graph every single point on this curve, okay? That's why we have those key points that we learned before. It's just to use them as prox. Okay, so 1 goes to a 2, and the 2 goes to a 4. Now, I prefer doing things graphically, but you can, like I said, go through the table of values. So we'll remind ourselves of the key points. We had 0, 1, and 4. And the f of x was at 0, 1, and 2. So once I go doubling all those y values, the x I'm going to keep the same, 0, 1, 4. But what happens here with the g of x? What values do I expect? Sorry? Yeah, 0. I'm going to write it as 0 times 2, but yeah, 0. And then 1 times 2, which is 2. And finally 2 times 2, which is 4. Okay? Which is exactly the points we got.
Why 2 times 2?
Because this is the value I have at the top. So g of x is 2 times f of x. So if f of x is 0, 1, 2, then this one here is 0 times 2.
Shouldn't it be 4 times 2?
No, you're times one.
I see.
You're just taking this value 2, and that translates over. It's early on Wednesday morning. Okay, so I'll give you a chance to think about this one, but we'll go back to it and discuss it, okay? So just look it over, do the same thing, okay, that we did there. But in this case, the transformation will go under the x, okay? There is a way to take this out, right? Write it as root 2 times root x, and look at it as a vertical stretch, but that might not be the most convenient way, okay, in terms of graphing. So you might want to look at it as an x transformation, right? Along the horizontal, not the vertical. Now freeze it. And we'll graph it on the same graph there, just in a different color. Okay, do you need a few more minutes? Would anybody like to come to the board, play around a little? No? Yeah. Okay, so what would be a good way to think about this? Before we said we can look at this as f of x, right? So it's the y that changes, but in this case, it's the x that changes, right? So when I do my table of values, if I have my original function here, once I draw the function for the other transform function, I'm going to keep the y fixed, because it's the y that doesn't change while the x changes, okay? So if I have my y fixed values, all I have to do is work backwards and figure out the x value, right? So if I go in the expression here, if y is equal to root 2x, then what is x? So I'm going to solve for it going backwards in a way, okay? So if I write there just for the first line, I'm going to go with 0 is equal to root 2x. So if I solve for that, what do I get for x? 0. Okay. The next one would be 1 is equal to root 2x. So first I need to do what there? Probably square the whole thing, right? So we get a 1 is equal to 2x. So the x will be 1 over 2. Okay. So if I place it in here, we have 1 over 2, and the first one was 0. Let's look at the last one where we have root 2 is equal to 2x. So this becomes now 4 is equal to 2x. So what is the x in this case? 4 is equal to 2x? 2. Okay. So let's see if we graph those. The 0 once again stays put. The 1/2 1 is here. And the 2, 2 is over here. Okay, so graphing this whole thing, this was called h of x. And we'll leave this in gray. You don't have to show the work all the time, because now we're going to discuss the pattern that happens here. Okay, so what do you notice? You're not comparing this to the red function, you're comparing it to the f of x. So at this point, we said we're keeping the y constant, so I'm staying on the same y line. I'm picking this point because it's easiest to graph. So we have 1, 1. What happened if I went to 1/2 1? Along the x. Times 1/2, yeah, or divided by 2, right? It went from here to half the distance. And this one here went from a 4 to a value of 2, right? So again, it's divided by 2. In other words, compressed. right? So it's a horizontal compression along the x-axis. You don't have to stay along the x, but it is a horizontal compression. So horizontal compression, and you can think of this as the y stays constant and the x changes. So x changes while the y stays constant. So even though we did the table of values here, once you have the graph for the parent function, you can easily read off just the crucial points and graph that way. You don't need this table of values at all times, right? And once again, you're comparing this, I'm going to draw an arrow. You're not comparing it to g of x, you're comparing it to f of x. Okay, and f of x and g of x, those are the transformations that we drew. And the key points, but everybody remembers the key points, right? For the parent functions we did last class? Raise your hand when you're done. We can move on to the next one. Done. Okay. Okay. Well, you can start this one if you want. Again, there are two ways to look about this. In this case, you can keep it as it is, but because it's a quadratic and there is a vertical happening if I take this outside, I would treat it as a vertical. But it's really up to you, right? If I look at it as it is, it would just be a horizontal stretch. Okay? Because before we had 2x, now we have half x, so that was a compression. This is a stretch. But if I take the 1/2 out, then I can look at this as 1/2 all squared times x squared, right? I'm just distributing that exponent. So if I see that as 1/4 times x squared, I don't have to worry about the transformation horizontally. I'm just going to worry about the vertical, right? Because once again, this was our 1/4 times the parent function. And in this case, since this is already called f of x, I'm going to call the parent function p of x. And we'll say that's x squared, right? That's what I'm comparing it to. But I will note here in gray that you can also read this off as a horizontal stretch, okay, because of that 1/2. So if you keep it in brackets, but I can also interpret it as a vertical compression because of the modification I just made, okay? So that's the nice thing about compressions and stretches. They are interchangeable. It just depends on where you modify your constants to go to. Okay, so let's draw the parent function. We'll try to do this without table of values if we can, right? So what are the points in the quadratic function? Yeah?
How do you know it's compressed or stretched?
So we talked at the top about a compression. We'll summarize at the end. But remember here, we're going at twice the value of y. That was a stretch. If it goes fractional, right, I'm going to a quarter of what the distance was before. So that has to be a compression, right? The point will go below 1. But we'll summarize in a bit. For now, just think of what happens to y. So it shrinks from the original value to a fourth of the original value. So if we have our parent at 1, 1, 2, 4, and negative 1, 1, and negative 2, 4, this is p of x. Is there a question, Arnav?
No, Nicholas just made a math joke.
Okay. Do you want to share it with the class? I think everybody needs a joke.
He drew it, he didn't draw it directly because he thought there was a radical in the function.
Okay.
And I told him this, and he just flipped it.
Okay. That is correct. A correct transformation. Okay. So we have our p of x, and once again, we enhance those 5 points. So I'll let you give this a go first. So we're treating it as a vertical compression. So what do we have to keep fixed if it's a vertical compression? I'm going to go... Well, 0, yeah, that stays fixed. But we said whenever we modify one variable, the other one stays fixed. So in this case, because y changes, what am I going to keep fixed? The x. So I have these invisible lines here. So I'm going to treat these points that line up with this. You don't have to draw these. Okay, they're just reminders. So these points are the ones I want to focus on. So those points will move down those lines because it's a vertical compression, right? So if, let's say, the color green, we're going to a fourth of the value. Who would like to come to the board and show us where the points travel to? It's exciting. I'm not trying to complicate, I'm actually trying to make it easy. So these points have to stay on these lines here, right? So whatever vertical transformation happens, they will travel up or down these vertical lines. If it's a compression by 4s, what happens to each y value? This one's a value of 4. Yeah. So from 4 goes to 1. Okay. So we'll jump to down here. And then this one here is already at 1. So where will it go? A quarter. That's right. Okay. And we'll do the same on the other side. And there it is. You don't need more than those points that you have there. Just be reasonable in extending it outwards. Nicholas, act professional. Okay, so this would be my labeled f of x. So you notice that these names are not set in stone, right? P of x, f of x. You set the parent function for whatever you want it to be as a name. Just don't override the givens in the problem. So p of x, f of x. Now, can somebody convince me that it's also a horizontal stretch? Do it visually. You don't have to do this algebraically. It's a bit painful, but visually, can somebody try to convince us that there's a doubling of the x value? What would I need to do? So right now, I set up to look at these points being compressed, but I can also look at it as a vertical stretch. Anyway? Okay, tell them. Come to the board and show it. What happens to what point and it goes where?
This point.
Yep.
Is this way.
Yep.
And down and forward.
That's right. And the one at the top? Oh, we don't have others. No, that's...
This one could be here.
Yep, that's right. So, yep, you're staying on the same y value, right? So from an x of 1, we're going to an x of 2. So you can also look at this as a horizontal stretch by 2. But it really doesn't matter what you do. At the end of the day, choose 1. Okay? Okay, I'll give you a moment with g of x is equal to 3x squared. Okay, I'll freeze it, but I'll do it at the same time. Once again, you can use your table of values if you want, but a lot of the times it's easier to just do it on the graph. It doesn't look like this is easy to graph, actually, because it's a 9x cubed, right? X squared. And, okay, so you can either look at this, as we said before, as if you leave these brackets untouched, then this is a horizontal compression. You can see it that way. But if you square the 3, this comes out, and you can see it as 9 times the parent function, right? 9 times the p of x, which shows you that it's a vertical stretch. So the 1 would go to a value of 9 at the top, which I'm just going to label here. Okay, and we'll say that's a 9. And this one here is a 9. Okay, and that's good enough. G of x. For horizontal compression, you take this point, and it goes to a third of its value, right? So this here is 1 over 3 along the x-axis. You can think of it that way, too. Once again, you don't need to draw these lines. They're to fix the direction in which you're trying to treat this transformation. Okay, you pick either vertical or horizontal for yourself, but you don't need to draw these. Okay, they just help you focus it in. Okay, so we're going to white out the relation here at the top because we're not talking about all of them for now. Okay, and we'll remind ourselves of all of them right at the end. So we said if the a is greater than 1, okay, if I have a g of x where a times f of, let's say, kx. Okay, so I'll have the a outside, then I know it's a vertical compression. So this is the parent function at all times. Okay, it could be a square function, quadratic, it could be a radical, a rational, any function, so parent function. If I write it like this, if the a is at the front, I'm multiplying all the y values that I had previously. And if the a is greater than 1, then I'm talking about a vertical compression. But if it's in between 0 and 1 or fractional, then what do we have? A vertical? Oh, it's the other way. So compression goes here, and we have our stretch for a greater than 1. Yeah. Yes, I said we're replacing that because you also have 2 others we haven't discussed yet. We'll do those next time. So just replace that with this. Okay? It's the same idea, but we're not doing the addition and the subtraction today. We'll do them next time. So vertical stretch and vertical compression, k is greater than 1. Then what happens here? The transformation is for sure horizontal because I'm looking inside the argument of f of x, right? So the independent variable. So that changes. It's automatically a horizontal transformation. And it usually opposes whatever happens vertical. So if one's a stretch, the other one is a compression. And same here, horizontal stretch. And we'll make a note at the bottom also about vertical, that's the A. In terms of reflections, okay, if A is negative, then you're reflecting about the X. And if the K is negative, then you're reflecting about the y-axis. Okay. Please don't try to memorize this chart. Okay, it's a reminder and a good summary of what we've done, but it's best to always think of what the parent function is and what's happening in the transformation. Okay? If you just keep it simple to literally the x and the y values, it's a lot easier than trying to remember all of them. The rest is individual work, but I will go along with you just if you're having trouble, okay? And show you maybe some of them could be written in different ways. Okay, so I'll go along, but I will give you a few minutes to set up. So here we're talking about the rational function. Does everybody remember what that looks like? Or should we draw the parent one together? Yep, it's almost like still two arms, but they're separated, right? We have, what did we learn last class? The new term? Asymptotes, okay? So it's the one function that has asymptotes. Sorry? Okay, so we're going to write, the first one I'll help you with. So we have 2 times 1 over x, right? I can look at it that way. And I know that 1 over x, so the parent, because I'm using f of x, I'm going to say parent is 1 over x. I'm going to automatically write down my asymptotes because for the rational function, oops, not restrictions, but asymptotes. The horizontal and the vertical. Okay, so if I draw that, I said I always need to label my asymptotes, so that would be the y0 and the x0. The function never goes through those. And then what were the crucial points? Does anybody remember on the rational function? What did we focus on? Okay, Rebecca? 1, 1, and negative 1, that's right. And then what steps do I take left and right of that? It's very symmetric. It is correct. What's this one here?
1 over 2, 2.
Yep, at 1 over 2, I'm at 2, and at 2, I'm at 1/2. And likewise here. And always make sure to extend it a little bit past those 3 points. But again, I need to enhance those because those are the ones that I need to show very well transformed, okay? So this is the p of x. You don't need to label it top and bottom, okay, as long as you use a bit of a color code. And now what happens with this, what is it, f of x? Does the x or the y change? The y. Okay, and what happens exactly from the parent to this function? If the y changes, it's a vertical, sorry? I don't need the whole word. Okay, vertical what? Stretch or compression? It's a stretch, right? All the values go to double their original value. So all I need to do is stay on the same x lines, right? So for this one, this point goes from 2 to where? 2, 4, and then from 1 to 2, and here we're going to 1. That's right. Okay. So 2 goes to 4, 1 goes to 2, and 2 goes to 1. So it won't look as dramatic as some of the other transformations you'll see, but you should still see a bit of a difference. And same with this one, goes from -1/2 to -1, -1 to -2, and -2 to -4. Okay, so that is our f of x. Once again, for this one here at the bottom, you can look at it as a horizontal transformation if you leave it as it is, or you can look at it as a vertical if you rewrite it. So this one's optional, it's up to you. So either 1 over 3 times 1 of x, or 1 over 3x, right? So this one tells me it's a horizontal. Stretch or compression? Compression, and here I have, actually not those brackets, but these brackets, so we can see the original function, and we have here a vertical compression as well. Okay, so there is no real pattern. It really depends on the function. So p of x is still 1 over x, and we have the same asymptotes as before. I'll just share them with both of these. Okay. So 1 over 3, not the nicest value, but do your best.